Do 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 do.
Good morning, America. My name is Garam Kim.
And I'm Danny Oscar.
And we are NASA TV. Let's get started. First off, NASA has been improving our technological exhibits at the Great Lakes Science Center in Cleveland to further enhance the learning experience for the local youth.
Wow, that is amazing.
Absolutely.
On a second note, NASA Glenn Research Center has given us permission to discuss the current and ongoing research at the Icing Research Branch. Here live is Graham Droon from NASA Academy 2013 to lead this discussion.
Thank you, Danny. The NASA Glenn Research Center has been doing icing research for the past several decades. One such research technique that they use is to use the twin-otter aircraft that's right behind me. At the nose, there's a camera mounted that takes pictures of the wing during flight. And as we move further down the aircraft, along the wing, they have chord-wise measurements that enable researchers to see how far the ice grows down the wing. And if you move further down the wing, you've got hard points where researchers mount various probes to determine the liquid water content and the drop size of the cloud that they're trying to characterize. And this section right between these two metal cups is a section where the camera takes pictures to determine the ice shape and the thickness of the ice to characterize which cloud conditions form which icing shapes. And now we'll head to the icing research wind tunnel to see what kind of experiments they do there. Here I am inside the icing research wind tunnel. Behind me you can see a heat exchanger and various spray bars and allow the researchers to simulate an icing cloud condition. And when researchers want to do experiments, they come into this control room here. The operator is able to set various parameters such as the air speed, the air temperature, the liquid water content, the cloud droplet size, and the duration of the spray time. And with varying these parameters, researchers are able to develop different ice shapes. And traditionally, after the experiment is done, the researchers would come inside the 6-foot by 9-foot wind tunnel and take this cardboard cutout to trace the 2D cross-section of the icing accreted shape and then digitize it to get the full icing geometry. But with technological advancements and the requirement of this new 3D laser scanner, researchers are able to collect a cloud of data points of the icing accretion shape, and now we'll go and see how this data is post-processed to create the full 3D geometry. So here's Lloyd, who's a summer intern working in the icing research branch. He's going to show us how post-processing of the data that's collected from the wind tunnel is done. So Lloyd, can you show us exactly what you do?
Yes. So we receive data from the IRT laser scan data. We receive them as a point cloud here. You can see there are millions of points. These millions of points are processed into a watertight mesh. As you can see here, they are not watertight at this point, but they are processed into a mesh, and then they are further processed into a watertight mesh.
Awesome. And what are these models here?
Well, once we have a watertight mesh, we can take that STL file and turn it into, or merge it to an ice-accreted wing representation, and then this is rapid prototyping of that model. This is done for aerodynamic testing simulations.
Excellent. And we can also take the geometry model that Lloyd produces and do computational analysis using CFD codes. And here we have another summer intern, Daniel Alhazen, who is another member of the NASA Aeronautics Academy of 2013 here at Glenn. Danny, can you show us what's on your computer screen?
Definitely, Graham. So now that we have our STL files created by Lloyd, we can import these into pointwise. 2D and 2D extrusions of ice accretion models have been simulated in CFD before, however, not to the complexity of the grid that you see here. Once we have our surface grid created, we can create the volume grid that surrounds it. With this grid, we can then export it to NCC, which is our CFD solver, and analyze our converged results. As you can see here, this is pressure contours, and by further manipulating the data, we can analyze other variables as well as the streamlines around the airfoil. Furthermore, we can extract boundary values at the airfoil and analyze the data, such as the pressure coefficient shown here. The dashed lines is our CFD solution, and the solid lines are the wind tunnel. As you can see, our data correlates very well, however we still have further refinement to do.
Thank you for joining us on our brief tour of the Icing Research Branch, where we are using various research techniques to investigate the effects of icing on aircraft performance. This has been the NASA Aeronautics Academy of 2013 here at Glenn Research Center, and I will now pass it back to you, Danny.
Thank you, Grom. That was amazing. NASA's doing amazing research. Do you have any concluding remarks?
I do. I'd like to emphasize the importance of the research that we saw today. Icing research is a very important part of aviation industry, as icing is a huge safety concern for pilots and passengers that fly on airplanes across the world. So I'd like to thank NASA for doing state-of-the-art research to further improve our understanding of how icing affects the aerodynamic performance of airplanes. So this has been NASA News. My name is Garam Kim.
And I'm Danny Oscar.
And we'd like to thank you for joining us. You stay classy, NASA.